Welcome to this premium engineering explainer. Today, we're diving into literally one of the most fascinating nanoscale materials in all of modern chemistry, quantum dots. We're going to see exactly how these tiny powerhouses are fundamentally changing the whole landscape of advanced electronics and renewable energy. So imagine taking the exact same chemical substance, right? But just by shrinking it down, it suddenly shifts from glowing a deep, vibrant red to a brilliant blue. We aren't changing the chemical makeup at all. We are strictly changing its physical size. I mean, it sounds like science fiction, but this is the actual reality of nanoscale engineering, and it totally challenges what we intuitively know about how materials behave. Here's our roadmap for today's lecture. We're going from the fundamentals of quantum dots into synthesizing CdSe dots, looking at their applications, and then diving deep into quantum dot solar cells, how they generate power, and wrapping up with a final revision and exam focus. Let's kick things off with Section 1, Fundamentals of Quantum Dots. So what exactly is a quantum dot? Basically, it's a nanoscale semiconductor particle, usually hovering between just 2 and 10 nanometers in diameter. To put that into perspective, that is literally smaller than a single virus. Now, unlike your standard bulk materials that have these continuous energy bands, these particles are so incredibly tiny that their electrons get trapped or confined in all 3 dimensions. Because they can't move freely, they develop discrete energy levels, kind of like individual atoms, and that's exactly why scientists often call them artificial atoms. Now, take a look at how this visual actually proves the physics of the quantum confinement effect. If you look at the bulk semiconductor on the left, you'll see it has a fixed band gap. But as we move over to the right and shrink that nanocrystal, the confinement width shrinks too. Because we're squeezing those electrons into a much tighter space, their energy levels are forced further apart, which widens the band gap. So a smaller dot gives you a larger band gap, spitting out higher energy light, like blue. On the flip side, a larger dot means a smaller band gap, giving us lower energy light, like red. Which brings us to the absolutely crucial mathematical relationship here. Your band gap is inversely proportional to the square of the particle size. Think about that for a second. If you just have the radius of your quantum dot, the band gap doesn't just double, it shoots up by a factor of 4. This little equation is the absolute cornerstone of quantum dot physics. It tells us we can tune a material's color and optical properties purely by changing how big it is. And there's another wild thing that happens at this tiny scale. The surface-to-volume ratio completely skyrockets. If you take the surface area of a sphere, which is 4 pi r squared, and divide it by the volume, 4/3 pi r cubed, you're left with a ratio of 3 over r. As that radius gets closer and closer to 0, that ratio just explodes. What this means in the real world is that a massive fraction of the atoms are sitting right there on the surface. This makes these artificial atoms super chemically reactive and incredibly sensitive to what's around them. Okay, moving right along to Section 2, Synthesizing CdSe quantum dots. So knowing all that physics, how do we actually make these things? Well, we use a wet chemical synthesis method. It's kind of like a very precise recipe. Step 1, you prepare a cadmium precursor, like cadmium chloride, alongside a selenium precursor. Step 2 is the exciting part. You rapidly inject that selenium into a hot cadmium solution. Bam! That instantly triggers nucleation, where the cadmium and selenium ions react to form tiny CdSe nuclei. Then in Step 3, these little particles grow as more atoms deposit onto the nuclei under super strictly controlled temperatures. Finally, Step 4 is surface passivation, which we use to lock them in and stabilize them. Let's pause on that final step for a second because it's super important. We have to cap these dots with organic ligands like topo. Remember that massive surface-to-volume ratio we just talked about? That makes our nanoparticles crazily reactive. If we didn't have these ligands attaching to the surface, our quantum dots would just instantly clump together, or aggregate, and lose every single one of those awesome quantum properties. Plus, these ligands help control the growth rate, boost structural stability, and even improve the optical efficiency by smoothing out any tiny defects on the surface. Next up, Section 3, Quantum Dot Applications. Because we have this incredible ability to tune their exact emission colors and absorption profiles, quantum dots are literally revolutionizing entire industries right now. Take your living room, for example. QLED TVs use these exact quantum dots to convert standard LED backlights into insanely pure, bright colors without the risk of screen burn-in. In the medical field, their bright, size-tunable glowing makes them absolutely perfect for highly precise biomedical imaging. But honestly, where they hold the most world-changing potential is in next-generation solar cells. which perfectly tees up Section 4, quantum dot solar cells. Now this table right here, this is a critical exam note. We're mapping out the architecture of a quantum dot sensitized solar cell, a QDSSC, layer by layer. Think of it like a sandwich. At the core, you've got the quantum dots, acting as your light absorbers. They're sitting directly on a porous layer of titanium dioxide, or TiO₂, which acts like an electron transport highway. Then you absolutely need an electrolyte, usually a polysulfide redox couple to regenerate the charge in those dots. And finally, a counter-electrode, generally made of platinum or carbon, to complete the whole electrical circuit. Let's see it in action in Section 5, how QDSSCs generate power. This graphic brilliantly illustrates the complete electron flow. Just follow the path with me. First, some light strikes the quantum dot over on the left. The dot absorbs that photon, and thanks to its specific band gap, an electron gets excited, jumping right from the valence band up to the conduction band. Because the energy levels align so perfectly, that excited electron is instantly injected into the porous TiO₂ network. From there, it travels out through the external circuit, powers our light bulb, and eventually arrives at the counterelectrode. Meanwhile, our original quantum dot is now oxidized. It's down an electron. So the polysulfide electrolyte rushes in, donates an electron to reset the dot, and the whole cycle just keeps spinning endlessly. You might be wondering, why go through all this trouble when we already have perfectly good silicon solar panels everywhere? Well, look at the graph on the left. Traditional silicon misses a huge chunk of high-energy ultraviolet light and completely ignores low-energy infrared light. It's just wasted potential. But now, check out the graph on the right. By engineering a tandem cell where we combine perovskites to grab the UV and visible light and tune our quantum dots to specifically absorb the near-infrared, we drastically cut down on that wasted solar energy. We are quite literally engineering artificial atoms to harvest the exact wavelengths of light that standard technology just leaves behind. It's a total game changer. All right, let's bring it all together in Section 6, Final Revision and Exam Focus. This right here is a classic test of the confinement effect. Imagine you have two dots made of the exact same material, cadmium selenide. Dot A is tiny, just a 2 nanometer radius. Dot B is a bit larger, with a 6 nanometer radius. Think about it carefully for a second. How do their band gaps compare, and which one is going to emit the shorter wavelength? The model answer here requires you to clearly state the logical flow. Let's break it down. Dot A's smaller size creates tighter spatial confinement. Following our physics rule from earlier, this results in a significantly larger band gap. And because the band gap is larger, the energy emitted when an electron drops back down is much higher. In physics, higher energy mathematically translates to a shorter wavelength, putting it right toward the blue end of the spectrum. Conversely, dot B is larger, so it has a smaller band gap and ends up emitting a longer, redder wavelength. If you want to secure full marks on a question like this, you have to ensure your answer explicitly contains these exact scientific keywords. You absolutely must mention the quantum confinement effect. You need to write out the equation, band gap is proportional to 1 over r squared, and you've got to explicitly state the inverse relationship between energy and wavelength. Doing this proves to the examiner that you truly understand the underlying mechanics, rather than just memorizing the final result. I highly recommend taking a quick screenshot of this revision sheet because it beautifully connects everything we've covered today. We started with the hard physics of spatial confinement and the inverse square law of the band gap. Then, we mapped that right onto the wet chemistry needed to actually synthesize and passivate these superreactive nanoparticles. And finally, we engineered those chemical products into the architecture of a fully functioning tandem solar cell. It's the whole shebang on one slide. It really leaves you wondering, doesn't it? As we get better and better at this level of nanoscale control, literally tuning our materials atom by atom to catch every single photon the sun throws at us, what other seemingly impossible technologies are just one quantum dot away? Keep studying, keep questioning, and I'll catch you in the next Explain.